The proposed research introduces a novel two-stage image inpainting method, SketchRefiner, which leverages user-provided sketches to refine and guide the inpainting process. In the first stage, a cross-correlation loss function is utilized to robustly calibrate and refine the sketches in a coarse-to-fine fashion. This approach effectively utilizes sketch information, eliminating artifacts caused by freeform sketches. The second stage involves learning to extract informative features from the refined sketches and modulate the inpainting process. The paper also discusses the use of sketches for image inpainting, highlighting their advantages over edges. It presents a novel approach, SketchRefiner, which addresses the misalignment and incoherence of sketches through a registration module and an enhancement module. A cross-correlation loss is introduced to penalize intensified differences in regions of the refined sketches. Furthermore, the research proposes a sketch simulation algorithm to simulate sketches from detected edges, targeting the characteristics of the sketch domain. This algorithm warps detected edges to simulate misalignment and composes the warped sketches with edges in valid regions to imitate incoherence. The paper concludes by outlining the pipeline of the proposed method, which includes a sketch refinement network and a texture restoration module. It emphasizes the importance of precise signal supervision and the use of sketch feature aggregation blocks for modulation of the inpainting process. Experimental results on public datasets demonstrate the superiority of SketchRefiner over state-of-the-art methods, both qualitatively and quantitatively. This research reinvestigates the challenges of sketch-based interactive image inpainting, targeting the characteristics of the sketch domain, and establishes a new benchmark for sketch-based image editing. The research paper introduces a novel approach to sketch-based image inpainting through the development of the Sketch-Modulated Image Inpainting Network, SIN, and a two-stage system, SketchRefiner. This approach focuses on enhancing the quality and realism of image restoration by leveraging sketches to guide the process. Key components include the Partial Sketch Encoder, PSE, Sketch Feature Aggregation, SFA, blocks, Texture Restoration Module, TRM, and specific loss functions. The proposed method is evaluated both quantitatively and qualitatively, comparing it with state-of-the-art image inpainting and editing methods. Results demonstrate the effectiveness of the proposed approach, outperforming other methods in various metrics. SketchRefiner consists of a sketch restoration network, SRN, and a sketch-to-image network, SIN. SRN refines the input sketch to align it with the image, while SIN fills in the missing regions based on the refined sketch. Ablation studies are conducted to evaluate the effectiveness of SRN's components, such as local contrastive loss, LCC, edge map, M, and region map, ERM. These studies show that LCC, M, and ERM are essential for handling complex structures and misalignments. Further ablation studies are conducted for SketchRefiner's SketchRefiner module, which refines the input sketch. These studies demonstrate that SRN plays a vital role in bridging the gap between sketch-like inputs and image inpainting methods, and that SketchRefiner's performance improves significantly with SRN. The paper also introduces a SFA block, which aggregates extracted features as modulation in SIN. Ablation studies show that SFA is essential for preventing high-frequency disorder and performance drops. The paper concludes that SketchRefiner has great potential in real-world applications but is still limited by its tendency to over-refine sketches with meticulous structures. Future work is anticipated to balance the requirements of sketch controlling ability and tolerance of sketch randomness. The authors provide a comprehensive review of the existing literature in image inpainting, generative adversarial networks, and sketch-based image synthesis, citing works on partial convolutions, gated convolution, and transformer-based models for image completion. The references also cover contour detection and completion, texture synthesis, style transfer, and image manipulation using sketches. Additionally, influential papers on deep learning, computer vision, and machine learning are cited, including those on progressive growing of GANs, spectral normalization, and batch normalization. The supplementary materials detail the implementation of the sketch simulation algorithm, loss functions, and training strategies for the proposed technique and retrained methods. The network architecture of the Sketch Refinement Network and Sketch Modulated Inpainting Network is also presented, comprising the registration module, enhancement module, partial sketch encoder, and texture restoration module. The authors discuss potential limitations and challenges in sketch refinement, including handling large mask regions and refining meticulous structures. Extended experiments are presented, including a user study demonstrating the superior visual plausibility of SketchRefiner compared to other methods, and model scalability experiments on Celeb AHQ, showcasing the technique's performance when combined with other state-of-the-art methods. The references provide a comprehensive overview of the state-of-the-art in image inpainting and sketch-based image synthesis, demonstrating the author's thorough understanding of the existing literature. The supplementary materials offer a detailed explanation of the proposed approach, highlighting its technical contributions and potential applications. Here is a combined summary of the 4 pages. This research introduces the novel concept of sketch refinement for interactive image manipulation and scene editing, proposing a new model called SketchRefiner to refine user-generated sketches and align them with the original image's edges and textures. The authors also introduce the Progressive Sketch Refinement Network (PSE) framework, which utilizes a coarse-to-fine guiding effect to provide multidimensional information in different granularity, significantly improving the performance of sketch-based image inpainting methods. Ablation studies are conducted on the architectural design of the proposed SFA blocks and the coarse-to-fine guiding effect of PSE, demonstrating the effectiveness of the proposed approach in enhancing the quality of sketch-based image manipulation and scene editing. The results are shown in Table 6, Figure 10, and Figure 11, illustrating the superiority of the proposed approach over other state-of-the-art methods such as Deep Fill V2, ZITS, and SketchEdit. The test protocol consists of samples comprising images, masks, and sketches, as depicted in Figure 12, designed to facilitate the evaluation of the proposed method's performance in various scenarios. The interactive demo, presented in Figure 13, enables users to upload an image, customize their desired mask and sketch interactively, and observe the resulting inpainted images in real time. The interface provides a seamless user experience, empowering users to iteratively refine their inputs and observe the resulting outputs, allowing for a comprehensive assessment of the method's robustness and flexibility. The proposed approach has been shown to be highly effective in enhancing the quality of generated images and scenes, outperforming other state-of-the-art methods. The interactive demo provides a practical application of the proposed method, allowing users to directly experience the process of sketch refinement and image manipulation. The proposed SRN architecture consists of a registration module, and enhancement module, both leveraging gated convolution, instance normalization, and residual convolution blocks. The refines the input sketch, while the enhances the registered face image. The partial sketch encoder, PSE, and texture restoration module, TRM, employ diverse normalization techniques and activation functions to preserve sketch details and restore realistic textures. Figure 14 illustrates the refined sketches and their corresponding inpainting results, demonstrating the module's efficacy. The SRN is applied to face manipulation and scene editing tasks, yielding impressive qualitative results as shown in Figure 15. This figure presents a series of images, each comprising an original image, input with a masked region and sketch visualization, and the resulting edited image. The top row showcases face manipulation outcomes, while the bottom row demonstrates scene editing results. The figure's layout facilitates a detailed comparison between original and edited images, highlighting the precision of the proposed method. The zoom-in capability allows for optimal viewing, further emphasizing the approach's capabilities in achieving accurate and desirable edits. The proposed methodology's significance lies in its ability to accurately edit faces and scenes, underscoring its potential in various applications.